Welcome back. So today we're going to be talking about the reactivity of these alpha-beta unsaturated species. Now, if you remember from the last lecture, and especially Monday's lecture, we can make these generally from the aldol reaction. But how is this useful to us? Well, we can react this with any nucleophile. In this case, I decided to choose CN, but you can react it with any nucleophile in this case. You react that nucleophile, we can get two different products. And so what we get is this thing called a 1,2 product, where instead of adding on to anywhere, we add onto the C double bond O in the middle right here. And so because of that, we make a new bond with the CN, and then we add an H using this workup, aqueous workup, and we can add the OH right there. And the reason why this is called 1,2 is because we have to go one species away, so onto the O, and go to another carbon away to get to the CN, between whatever we added here, the H, there we added at the CN. Okay, so that's our 1,2 product. However, we can add another product right here, which is a 1,4 product. Now, instead of adding onto the C, we add onto this C on the very end, or what we call the beta carbon. We can add a nucleophile to that beta carbon, and somehow this looks really weird. We just get missing a double bond, and somehow we still keep the C double bond. So how's this 1,4? Well, in reality, we do a tautomerization. We add the H over here, and we count 1, 2, 3, 4 carbons away to get to our CN. And so this, or 4 species away. And so this is how we can get to the 1,4 product. Now, it doesn't seem intuitive. Why can't we just add onto this beta carbon right over here? Usually we want to add onto the electrophilic C double bond O. Well, the reason why this is extremely important is because you can push all these electrons all the way up to the O when you're doing your mechanism. And so it's very important. And that's because it's conjugated. And so as an example, looking at this example, we can take this CN, move it to make this new double bond between this alpha carbon and C double bond O carbon, and move these electrons up right here to make this negative charge. And again, this is going to be our 1,4 addition, showing at the top here. Now, granted, there's going to be some rules that you'll have to keep in mind. All Grignard, so the MGBRs that we learned back in 8B, and the organolithiums, which we also learned back in 8B. These two will always add onto the C double bond O. And that means that it's always going to make this 1,2 product, or again, adding directly onto the C double bond O right over here. However, we can also get the 1,4 product, and that's only if we use milder bases or product solvents. So we'll see a really good example of what a milder base means in this case. Okay, so now we're going to start learning about the Michael addition. What my name is just really cool. However, so the first part about this is that instead of the nucleophile, like we learned in the previous slide, where our nucleophile was CN, in the Michael addition, that nucleophile is always enolates or enamines in this case, right? But how does that actually do an addition? So first off, let's make our enolate. So let's say we have this diketone right here. And again, the place that you would like to make your enolate is in the middle, using NaOH. Move this, and we can move it to make a new double bond. But we can just put the electrons onto this carbon. So we have a negative charge on that carbon, so that's pretty good. Now this is nucleophilic. Now we can add this, take this carbon, add it onto the beta carbon right over here of this species. So this vinyl methyl acetal. You take this double bond right over here, make a new double bond right here, move these electrons up onto the O. Now, note, we've made this new carbon-carbon bond that shows up right there. That's extremely important in how we're going to be looking at this reaction further. All right, so we have this, and if we do some aqueous workup, and then we also tautomerize it, we can now make this species right here with the new carbon-carbon bond between here and here. Okay, so that's good and all. Now, how does it react with enamines? Okay, so we've already learned how to use enamine reactions from 8B, as well as earlier last Monday. But how can we do that? And so every time we get an enamine, so the ene part and then the amine right over here, we can do a reaction on another beta carbon. And so let's say we have this beta carbon right here. We can take these electrons, attach onto the beta carbon, move these up to make a new double bond between the alpha carbon and the C on the C double bond O, move these electrons onto the O. And then just for extra stability, you take the electrons from N, make a new double bond right here. And so we get this crazy species right here, but the new bond, again, we made is between here and here. Okay, so what we can do is we can do an aqueous workup, or in this case, an acid workup, not an aqueous workup. We do an acid workup just to add the OH, and then we tautomerize it. And so again, we can make this ketone again with the new bond that we made in the previous step between here and here, and we still have that N, the N that shows up. Now, we can get rid of this positive N by adding water, and all we do is cleave that off, cut it off, replace it with an O. And this right here is our final product, with the new bond being made at this C-C bond. Right there. So that's how we can react it with enamine. And so keeping these two reactions in mind is how we're going to start doing even more reactions. Okay, so there's one more reaction that we've learned in this chapter as well. That's the Robinson annulation. So what is the Robinson annulation? Well, in general, all it is just a Michael addition plus an aldol synthesis, or another aldol synthesis. That's all it is. It's just the sum of these two reactions. But how does that actually look in practice? Well, first off, what we do is we can make an enolate from this, adding an OH. I won't draw the mechanism here, but showing this, making an enolate, we can attack this beta carbon right over here. And then after a bunch of proton transfers and polarizations, we can get to this species right here, between this number 4 and 5, the carbons 4 and 5. Now, adding this carbon right here, this is going to be your Michael addition, your Michael reaction. And so this will be your first step in this reaction. Now, the reason why I've labeled this as 1, 2, 3, 4, 5, and 6, where 1 is always going to be your alpha carbons, and 6 is always going to be another ketone or another carbonyl, is because this combination of these two with the two H's right here and this C double bond O, we can attach these two, make a new bond between 1 and 6. And that means we can cut this off, cut off these two H's, and add a new double bond right here, or add a new bond right there. And so your first step, again, always is going to be making an OH. And so we've made this new bond between 1 and 6 right over here. And again, now you see why I numbered it, because we started the alpha carbon that we had, 1, 2, 3, 4, 5, 6, and that was where we originally had our C double bond O. Now again, this is the initial product, but if we add heat, we can cut off this OH right here, and then add a new double bond between 1 and 6 again. And then what we get is this new double bond between 1 and 6. So these two steps right over here is going to be our aldol. And so the sum of these is going to be equal the Robinson annulation. Now remember, annul means ring. And if you saw, we actually made this new ring right over here. Between 1 and 6, and this new 6-membered ring with an alpha beta unsaturated ketone. Now, the only rule for the Robinson annulation is that it only makes 6-membered rings. It only makes 6-membered rings. It doesn't make 5, doesn't make 7, it only makes 6. And so that's a very key important step right here. But this is how we can use different additions or the allosynthesis together. All right, let's do some practice problems. Okay, so first we want to know what the product between this acetone and whatever this species is, and we just add some H2O plus. And so our first step is NaOH. Well, the purpose of this step is to make this enolate right here. You're going to get some enolate that shows up. And now we have this enolate, we can react it again with this carbon right here. Now we can react it many places, like this C here or this C, but we have this beta carbon right over here, which is ripe for the picking. So what we can do is take that, react this onto here, and after a bunch of different steps, what we can get is that same molecule or close to it. But instead of having a double bond now, we have that extra carbon. And so I'm going to label this carbon as 1 and 2. And so we have 1 and 2. And then we can get adding the carbon from the acetone right here. And so, oh, let me do that again. Yep, right here. Because in this case, I'll number this. This is 1, 2, and 3 in blue. We made a new bond between this blue one and this green 2. 1, 2, 3, right there. This last step, again, is just for aqueous workup. But that's how you can view this, is that first you always do an enolate. Then we add the nucleophile and the electrophile together. And then we do some aqueous workup. And so the new bond, that, again, looking at this, new bond that we made is between that green 2 and this blue 1 right here. And so we've added this acetone group onto what is originally our electrophile. This was our nucleophile. This was going to be our electrophile. And so that's how we can do the first Michael addition onto products like these. Okay, so now we're going to go to a retrosynthesis, or what were our original 2 products, right? Okay, so looking at this product right here, what we can notice is that there is a 6-membered ring right here. And in fact, it's a very specific 6-membered ring because it has a C double bond O, and right next to it, C double bond C. This is going to be our alpha beta unsaturated ketone, which is what we can see from an aldol synthesis. But before I do anything, I'm going to label this one right here. So starting from this ketone, we labeled this as 1, 2, 3, 4, 5, and 6. Now, looking back at this retrosynthesis, we use heat and we use NaOH. Those are the 2 ingredients for an aldol synthesis. Now, how do we go back from an aldol synthesis? Well, first step is we cut the C double bond C right over here. Now, the carbon, or the alpha carbon in this case, that's closest to the C double bond O, that gets 2 H's. So drawing this molecule again, 2, 3. We have something with this extra methyl group right here, and we add the 2 H's onto that. Okay, that's one part. But the other, the beta carbon right here, we cut that double bond and replace that with a C double bond O. And so this will be our first product right here, where I'll draw this again, where we have that 6-membered ring that we didn't touch. Then 1, 2, 3. Methyl group, C double bond O. And so this is going to be our first thing. However, that was only step 2. We got to go back to step 1. And so labeling our carbons again, this will be 1, 2, 3, 4, 5, 6. Now, our first step, however, was kind of weird. It only says base. But how can we actually go back to that reaction? Well, if you look between 5 and 4, as we've always done with our reactions, we can make this, adding this to an alpha to another carbonyl right here, through a Michael addition. Now, going backwards, first we have to cut this bond between 5 and 4. And then one of the bonds from here, between 3 and 4 and 3, will get a new double bond. Whereas this one, well, that will just turn into a regular H. So our original products we get is going to be, this ketone and this alpha beta, oh, sorry, I forgot this methyl group right here. This alpha beta unsaturated ketone. Now, again, I'm going to label the carbons again. So this will be 1, 2, 3, 4. Now, the thing is 5 and 6 come from the other ketone right here. And so that's these are going to be our original reactants and how you should view some of these products.